More physics. This is physics so far, number 6. We'll get 2 or 3 of these into this video. See how it goes. So, number 6, we've got a block being pushed up a ramp, but the force pushing it is not in line with the ramp. It's horizontal like that. So we'll have to break that up into some components. So let's see. On the diagram below, draw and label all the forces. So I'm just going to do it as a dot here, and then I'll say that's the ramp angle. So I've got the force, the pushing force would be here, gravity, doing its gravity thing would be here, and the normal force would be here, perpendicular to the ramp, and there's friction. So we're pushing it up the ramp, so the frictional force would be that way. So those are the forces acting on the block. Develop an expression in terms of m, theta, mu, f, and g for the block's acceleration up the incline. Sometimes in these situations we are asked not to mess with this diagram. So if we want to break things into components, we should do it sort of on our own dime here. So I'm going to go ahead and do that. I'm just going to recopy stuff. The gravitational force I need to break up into components. Right, that would be theta there. And then the pushing force, which is horizontal here, I also have to break up into components. Break that up into this and this, and you got to be careful with the ramp angle. This would be theta here, right? If the ramp angle is, just look at the picture, those would be, what are they called? Corresponding angles, I think, are equal with the parallel lines there. Okay, so this is the force that's called F. So the components would be here, this would be Fg cosine theta, and this one would be Fg sine theta, or Mg sine theta if you want, and cosine theta. And this would be F, this is the adjacent, and this is the opposite, F sine theta. Right? And there's our normal force. So some things that we know here, the forces in this direction have to be balanced because the block's moving up the ramp this way. There's no motion in this direction. So that means the normal force has to be equal to the sum of these two, right? The normal force is balancing those two. Part of this pushing into the ramp is making the block seem heavier, right? The ramp. So that's going to be F sine theta plus mg cosine theta. Right? I don't know if I even need that right now. I think I need that later in the problem. So, but that's a fact, right? In the direction, oh no, maybe I do need it because I need to find the frictional force. So friction is equal to mu times the normal force, and that's this. F sine theta plus mg cosine theta. So I think I am going to need that, right? And then I know that the sum of all forces would be equal to, in the direction of motion here, I've got this Fg cosine theta, which is doing battle with these two, right? So it's F cosine theta, that's the up the ramp part of the F pushing force, minus the part of gravity, mg sine theta, that's down the ramp, but there's also friction, minus friction. And there's our expression for that. All right, so it's looking kind of messy. So mass times acceleration is equal to F cosine theta minus mg sine theta minus mu times F sine theta plus mg cosine theta. And then you want an expression for the acceleration. There it is in all its glory. And I don't think there's much you can do to simplify that. So I just leave that alone. And then C, develop an expression for the magnitude of the force that will allow the block to slide up the plane with a constant velocity. If it's going to move up the plane at a constant velocity, that means the forces in the up the ramp, up down the ramp, would have to be equal. In other words, the net force would have to be 0. So that would have to equal those. Or you can just go straight from this equation. It would mean that from our net force equation, if it's going to move at a constant velocity, the sum of all forces would be 0. Right, so this would have to be true. And an expression for the magnitude of the force. And I guess that they want me to, oh geez, it's just not pretty, is it? All right, so I'm thinking now I have to substitute here mg sine theta minus friction. So that's mu f sine theta. I'm going to distribute that minus sign through mu mg cosine theta. Okay, so if we want to find an expression for f, I could move these two to the other side. I'd have mg times sine theta. You can go through the algebra here in more steps if you like to make sure you understand this. Oh, hey, there it is. This work here equals, and then on this side I'm going to factor the f out. F times cosine theta minus mu sine theta. Right? And so f would have to be equal to mg times sine theta plus mu cosine theta over cosine theta minus mu sine theta. Right. And then they want to know what relationship must theta and mu satisfy in order for the solution to be physically meaningful. Well, this couldn't be negative, right? I mean, we're pushing this thing up here, so what that means, since we're talking about the ramp angle is between 0 and 90 degrees, so sine theta and cosine theta are positive numbers. So for it to be meaningful, this cosine theta has to be greater than this. The bottom of this would have to be positive. So cosine theta would have to be greater than mu sine theta. And there's different ways you can play around with that. You could say that mu would have to be less than the cotangent of theta. That would be one way to describe that relationship. Right? If mu is not less than cotangent of theta, then you can't push this thing up at a constant velocity. It's not possible. Right? All right. Number 7. This is a great problem, in my opinion. It's got a lot of Newton's third law. Now, there's a few different ways to approach this problem once we get into it. So, well, I'll start out and we'll see how many, if we want to do more than one approach, or we can talk about them. So on the diagram below, draw and label all the forces acting on each block. The block number 1 is on top. So it has the pushing force is on it, right? It's the pushing force is not on the lower block, it's just on the upper one. And we would have, of course, gravity, which would be m1g, and we would have, the friction is between the blocks, so there would be a frictional force here, and then there would be a normal force, m1g, here. All right? Second block is the tricky one. The second block, the downward forces on it, you could either just lump in and say, well, there's a downward gravitational force of both blocks, or maybe it makes more sense to say there's m2g here, and then the normal force is an interaction between two things. So if block 1 is pushing up on if block 2 is pushing up on block 1, then block 1 is also pushing down on block 2. So this is like a Newton's third law pair. That's an interaction between two objects. So why should we be thinking about Newton's third law? Because there's two objects here, and they're interacting with each other. And what else do we have? So then the normal force here would have to be equal to, would have to counteract both of those. And the frictional force is an interaction between these two blocks. So if there's friction here in this direction on this block, then there's friction here in this direction. And it is worth, if that doesn't seem right to you, it is definitely worth stopping and meditating on that for a little while. So just going back to the situation, thinking about what's going on here. If this block is being pushed forward, and there's friction slowing it down, then that frictional force is going to, it might have a small effect, but it's going to make this second block move forward, right? You think about if these were attached, of course, if you pushed on this one, this would move forward. But if it's very sticky, then it's going to make block 2, or mass 2, move forward. And why is it moving forward? Because the frictional force is equal and opposite to what it is on block 1, because it's an interaction between those two objects. All right, so there's our diagrams. Now, find the acceleration of each block, A1 and A2, relative to the horizontal surface. So I don't think I can find them in terms of numbers here, right? Because we just have our letters, so in terms of the given stuff. So the sum of all forces, sorry, that's a crappy looking sigma there. There we go. Well, that's not much better, but sum of all forces on block 1 would be equal to those are balanced, of course, and then there's those two. So the pushing force minus the force of friction. Right? And how much friction is there? Well, there's mu times the normal force, right? So that would be equal to mu. That's one of the letters they gave us that we're allowed to use, times the normal force, which is m1g. Sum of all forces is mass times acceleration. All right, so the acceleration of this block is F minus mu m1g all over, all over m1. And then for block 2, the sum of all forces on this one, it's just F, right? And I know that F is equal to mu m1g. It's equal to this, right? So I'm not recalculating it here. It's not equal to mu times this normal force, because that's an upward. That's not where the friction is, right? The friction's not between this block and the ground. So I'm using the calculation here and the knowledge from Newton's third law that those are equal. That's equal to mu m1g. So the acceleration of that block is mu m1g over m2. And let me subscript those, right? Okay, that's part B. Part C, in terms of L, A1, and A2, find the time t needed for the small block to slide off the end of the larger block. So in other words, how long does it take for the small block to get to the end of the other block? So this is where we have some choices about how we can do this. What we can do. Let's see. We could, because these accelerations are constant, we could approach this in a kinematics way, right? What we want is for we want to know when M1 gets from here to here, but this block's also going to be moving, so the total distance that M1 moves is going to be this distance. Let's say if we called that, it's going to be L plus however far this moved. So the distance that 1 moves is going to be the distance L plus however far block 2 moved. And then delta x2, of course, is just delta x2. Right? So we could do it, I think, with these. They both start from rest. So using that equation, the displacement of block 1, plus the length of that block would have to be equal to the displacement of block 2. Wait, I don't like that. Hold on a second. It seems like this one would be that I should have the plus L over here. Let's look at that again. So this is going to go, so I'm imagining here the block 2, the slab is here, right? And then this one is here, so I think that, yeah, the distance that this one goes is the bigger thing. L plus. Yeah, that's right. Oh, I just copied it down wrong here, didn't I? Whoops, sorry about that. So we were right the first time. That makes sense. So let me write that down again. Write it down right this time. Equals L plus delta x2. Okay, and since I have constant acceleration, I know that delta x is equal to 1/2 at squared plus vit, right? But both of them start out with an initial velocity of 0, so I can ignore that term. So let's set that up in this equation. So for delta x1, I have 1/2 times the acceleration of block 1 times t squared equal to L plus delta x2, which is going to be 1/2 acceleration is mu m1g for m2 times t squared. Right. So we're trying to solve for t here, right? So I think I need to get these t terms together. Let's multiply the whole thing through by 2. That'll get rid of the 1/2 and it'll turn that into 2L. So then, let's see, that would give me a really crazy looking expression here. If you can follow the algebra here. So I'm subtracting this term over to here and then factoring out the t squared. And it would help if you could see that, wouldn't it? I subtracted this term over to here, factored out the t squared. right? And I've also multiplied through by 2 to get rid of the fraction. So there's a couple steps there. You don't have to do that in one step. And then, so T would be equal to the square root of 2L over this mess. And there's nothing really you can do to clean that up. So this is an ugly looking expression. But that's how long it would take. So there you go. All right. D, find the expression for the energy dissipated as heat because of the friction between the blocks. That's, I think, easier. So the energy dissipated as heat because of the friction between the two blocks is, since it's a constant force of friction, the work done by friction is equal to, it would be a negative amount of work, but if they say the energy dissipated, we're taking the positive version of that. So the work done by friction would be negative force of friction times distance, force times distance. So the energy dissipated is the positive version of this, which is the force of friction, mu m1 g times the distance, which is L, right? Because it's the distance that blocks rub against each other, which the block 1 is going to be dragged across a distance L. Oh, there you go. That is a messy problem by the end there. Well, we're at 22 minutes. I think we can maybe try to squeeze in number 8 here. So let's see. Block with mass of 10 kilograms released from rest, and it slides a distance of 5 meters down a frictionless plane. It's inclined at 30 degrees with the horizontal at the end distance of distance d. The block strikes a spring. The spring constant is 150 newtons per meter. Assume that the spring's ideal. That means we can use Hooke's law and all the stuff we know about springs. That the mass of the spring is negligible and the mechanical energy is conserved. They didn't have to tell us that. I guess so it's frictionless, right? In other words. Determine the speed of the block just before it hits the spring. So at the beginning, at the highest point, it has all mgh. And just before it hits the spring, if we take that to be the 0 point of this problem, which I think makes sense, then we have 1/2 mv squared there. So the m's cancel out, and I get that the velocity is equal to the square root of 2gh, where h is, if this distance is 5 meters, and this is 30 degrees, then this is 2.5, right? It's 5 times the sine of 30. Sine of 30 is 1/2. So that's square root of 2 times 9.8 times 2.5, which is 2 times 9.8 times 2.5, 7. So it's going 7 meters per second. Let's see. Determine the distance the spring has been compressed when the block comes to rest. So I know that at the beginning, when it just strikes the spring, it will have 1/2. So let me just draw a picture. Make sure you're on board with what I'm thinking here. So here, this is where it strikes the spring, and it's going to compress it this distance. Let's call that x, right? But it is going to drop a little bit in the process. Now that's still 30 degrees, so however far it gets compressed, it's also going to drop by a distance of 1/2 x. So I'm going to take this to be my 0 position, right? That's like my h equals 0 position. That means when it's right here, it's got 1/2 mv squared. It's got kinetic energy, but it also has a little bit of potential energy. It also has mg times that height, 1/2 x. And then when it gets down to the bottom, it's not going to be moving anymore, and it's at h equals 0, so all of the energy will be in the spring, 1/2 kx squared. Right? So let's see if we can do something with that. Mass was it 10? Velocity 7, we just found that. Mass is 9.8 times the height is 1/2 x equals 1/2, what's the k? 150 times x squared. So that looks like a quadratic thing that I'm going to have to deal with here. So let's clean up this. 49 times 245, I think, plus 49x equals 75x squared. I hope I didn't make any mistakes there. That's right. That's right. Okay, so that looks good. So I'm going to go ahead and graph that. So 245 plus 49x minus 75x squared. Get rid of the rest of that garbage. And I'm going to go back to my window because it's all crazy from the last time. I think that this is going to be a pretty small number, right? Between 0 and probably, well, it's not going to be more than the 5 meters, right? And go back to 1 for the scale. And then my y minimum and maximum, those are the, let's see, I guess I could just go back to the standard window for that, right? We want that energy to balance out, and let's graph it and see what happens. Boom, there it is. So second, calculate 0 between 2 and 3, but definitely between 0 and 5. 2.16 meters. All right. Determine the location with respect to where the block was released, where the speed of the block reaches its maximum value after the collision with the spring. Ha! This is familiar, right? We dealt with this problem before. We all had to correct it, I think, because we had a hard time with it. So, where is speed maximum? Speed is maximum when the derivative of this equals 0, and the derivative of that is acceleration. And since net force equals mass times acceleration, when acceleration is equal to 0, that means when the sum of all forces is 0. So when what's the condition there where the sum of all forces on the block is 0? Well, the sum of all forces on the block in the direction of motion, I have the spring force this way, and then part of gravity. Which part? The down the ramp part. That's the sine component of gravity, right? I've done that many times. So when those two things are equal. So it's going to happen when kx is equal to mg sine theta. That's where that position is going to happen. Right? So let's solve for that. So k, x, that's what we're trying to find. M, g, sine of 30 degrees is 1/2. So that position is going to be at 4950. Oh, x is equal to 0.33 meters. So the question is the location with respect to where the block was released. So that's going to be 5.33 meters from the release, right? Because it already slid down 5 meters till it got there. So 5.33 meters from the release. Now it's going to go another 2.16 meters after that, right? It's a big spring. But this is where the maximum speed happens. That's a good problem. I'm glad we got reminded of that situation. And then finally, part D, determine the maximum speed of the block. So what is the maximum speed there? Well, let's see. We could go back to our energy considerations there, right? We would have, let's see, at that position, I guess we know, let's see, there's a couple ways we could do this. We know what the total amount of energy is at any time, so we could approach it that way, couldn't we? Let's see. So I know that the whole, well, I guess it depends on where we take the h equals 0 height to be. Let's see, how shall we deal with this? You might take an approach that's different from what I'm about to do, and that would be fine, so long as you can get the right answer. Let's see, so what's going to happen is, let's do the energy, let's take this position, so let that be equilibrium. This is part D. Equilibrium, and then it's going to go 0.33 meters to here, and this is where the maximum velocity is going to happen. So since that's the lowest point it's going to be at that we're interested in this part, I'll take that to be my 0 height. Right? Now, when it hits at equilibrium, what I know here is the spring is not compressed yet, so there's no spring, no energy in the spring. I know that it's got kinetic energy, and in fact, I know how fast it's going there. That's where it's that's the 7 meters per second, and it also has a little bit of gravitational potential energy, right? That's the mgh. It's going to be half of 0.33. It'll be the sine component of this, right? Same as what we did before, and then when it gets to here, it's going to have 1/2 m. This is where it reaches its maximum velocity. So 1/2 m v max squared. I won't know what that is. Plus, let me scoot that over so you can see. Plus the spring is now compressed a little bit. 1/2 k x squared, where x is the 0.33. All right, so I think this will work nicely. So 1/2 m v squared plus m g. H is going to be half of 0.33, so 0.165 is equal to 1/2 m v max squared plus 1/2 k times x 0.33 squared. Sorry about the crashing in there at the end. All right, so let's clean this up. That's 245. We just did that. This is 98 times 0.165 is 16.17. Not going to round anything yet. 5 Vmax squared plus 75 times 0.33 squared, which is 8.17. I guess I'm going to round that a little bit. And so subtracting that over to here, looks like that's going to be 8, so that's 253, 5 You can do as much or as little of this in your calculator, whatever you want to do. So Vmax is equal to 253 over 5, the square root of that, which is 7.11 meters per second. So it doesn't attain a whole lot more speed than what it did when it hit the spring, but a little bit more. All right. There you have it. That's 6, 7, and 8.